Okay, so last week we had the first lecture, and the main content of that lecture was the definition of a category. So a category, as we found out, and many of you already knew, has objects and morphisms. And we had several examples of categories, and many of those examples were of the kind: the objects of the category are mathematical structures, and the morphisms are somehow transformations between the mathematical structures. And somehow the motivating philosophy for part of the usefulness of category theory for such examples is that quite a lot of the important properties of areas of mathematics can be captured as properties of structures and their transformations, so as properties of structures and their morphisms. And kind of part and parcel of that philosophy is the idea that when you define a mathematical structure, there should be some corresponding natural notion of transformation of that structure, some natural notion of morphism between them. So last week, I defined a mathematical structure, namely the structure category, that is a mathematical structure. So we should apply the philosophy of category theory to categories themselves and ask what the morphisms of categories are. And as probably many of you know, I mean, I know that lots of you have some background in category theory. This is still doing very much the fundamentals. The notion of morphism between two categories is a functor. So we're going to begin today with the definition of a functor. So a functor let me find a nicer pen. A functor, we tend to use capital letters for functors. And a functor is a transformation from one category, curly C, to another category, curly D. And it's a transformation of categories. It's the natural, if you were asked to define what the natural notion of transformation between categories is, you would almost certainly come up with this definition. It's just so driven naturally by the definition of a category itself. So what it is, so C and D here are categories. It's given by two pieces of data. We want to transform one category to another. Well, categories have objects and morphisms, so the most natural thing in the world is to map objects to objects and morphisms to morphisms in such a way that the mapping of morphisms ties up with the mapping of objects. So it's consistent with the mapping of objects. So we need to give a mapping of objects. That's simply going to be a function. So we'll use f again for the function. This is a function that takes objects of C to objects of D. But if one's being very precise, one might give this an index. So one of a name to say this is the function on object. So we could give it a subscript O to say this is the function on object. Or we could read this as 0. So actually, I'm going to read it as 0 because when one gets to higher dimensional category theory, which is something for later in the course, one starts to number these pieces of data. So we have a function from objects to objects, and we have, for every pair of objects, we want function from morphisms to morphisms. Morphisms are specified by their domain and codomain. So then you have a set of morphisms, the Home set for that domain and codomain. And we want the functions to work for every morphism given by every domain X and every domain Y. So for every pair of objects, x and y of C, we have a function f. Now it's a function of morphisms. So we might put a one subscript here to say it's a function up one level, the next level up from objects. If we're being very precise, we would label it also with the subscripts x and y. This maps every morphism from x to y. The most natural thing is to map it to a morphism in D well, we need an object of D to act as the domain, so we'll take f of x, and an object in D to act as the codomain, so we'll take f of y. So when I was motivating categories, I was saying you can view them as a bit like directed graphs with a composition operation on them. This is like a natural notion of also graph transformation or graph homomorphisms. So graph homomorphisms are mappings upon objects that preserve the existence of edges. Only with categories, we're not just concerned with the existence of edges, but our edges are directed arrows that have names to them, and there may be several directed arrows. So rather than just being concerned with existence, we're mapping the collection of maps from x to y, which have names associated with them. They have their own identities. Each one gets mapped to a map from f of x to f of y. And we're still ignoring something about a category here, is that a category had this data, objects, and morphisms, together with some further requirements that there should be the identity morphisms and that there's a composition operation. And so because we want to map the structure, to preserve the structure, we're going to require that we preserve those elements. So for every object x, in C, if we consider the morphism action on the identity object of x, that gives us that we're mapping a morphism from x to x, the identity morphism. That's going to give us a morphism from f of x to f of x, and we require that morphism to be the identity morphism in D on f of x. So this needs to be the identity morphism on f of x. And strictly speaking, let me keep these ones in black. And this is the 0 here, applying the object action here. So it preserves identities and it preserves composition. So for every pair of composable maps, F and G and C, if we take the morphism action applied to the composite map G composed with F, then we get the composite in D of the morphism action of F applied to little f, of the functor applied to little f, composed in D with the morphism action of F applied to, sorry, it should be G here. So f of G goes from f of y to f of z, and f the functor applied to little f, the morphism, goes from f of x to f of y, and so they compose together to give you something from f of x to f of z, which is the same type as this. And sorry, I want to keep on putting the subscripts here in. Well, let's even be very precise just for the definition. So here is f1 on the object x of z. Here it's f1 on y and z. And here it's f1 on x and y. But anyway, one's required to preserve identities and composition in this way. So essentially you have the data that specifies the functor, namely these two functions. Well, the function on objects, a family of functions indexed by pairs of objects in C, the action on morphisms, and they need to satisfy two properties. So just to say, this is called the object action, and this is the often called action on morphisms, or let's say morphism action of the functor. And it would be very fiddly to always write all these subscripts here. I was doing it just to be precise in the first definition, but from henceforth, I'm not going to ever write these subscripts. So that's why I put them in a different color. So none of the information in black. We're just going to infer that from the context from now on. Okay, right. So hands up, how many of you have seen the definition of a functor before? Okay, well, almost everybody. But anyway, we have to go through the basic definitions. We're starting the course from scratch. So anyway, let's look at a few examples. Let's see, I think I'm on button. Yep. I'm just going to consider a very few examples before going on to some further remarks. Using categories that we introduced in the last time. So the first two categories I introduced were the category of sets and the category of groups. There's a very obvious functor that goes from the category of groups to the category of sets. It's obvious because it does the following, very obvious job. But if we give it a group, so if we apply U to a group, so a group is given by a set G together with a multiplication operation M and an identity element E that satisfy the axioms for a group. If we apply, so this is the object action, if we apply U to such a group, we want to get a set back from it. Well, there's an obvious set to take here, set G. And if we apply, so this is the object part, the object action, and if we apply U to a morphism, well, a morphism in the category of groups is, we've got morphism between two objects, so it's a morphism between two groups, it's a homomorphism, as that's how the category was defined. So if we have a homomorphism from one group, GME, a homomorphism to another group, G prime, M prime, E prime. Well, what we're required to get is a morphism in set, that's a function from U of this group, the G group, to U of the G prime group. We need a set, we need a function from G to G prime. Of course, the homomorphism is a function from G to G prime, satisfies the further properties, but it is a function. So this is simply, so morphism get back is simply the function H from G to G prime. So this functor is so obvious and so basic, it's absolutely obvious that it preserves identities, it's absolutely obvious that it preserves composition, because composition of homomorphisms is just function composition. It has a name. Does anyone know the name? The forgetful functor, because it forgets the structure of a group. It remembers only the set. Very good. And a lot of categories are given the objects as structures and the function, the morphisms of functions of certain kinds, the identities of the identity function, and the composition is the composition of functions. We saw two other examples last week. So we also, for any such category, you have a forgetful functor just to the underlying sets. So we have a forgetful functor from topological spaces to sets that forgets the topology, and any continuous function is still a function on the underlying sets. And we also have a forgetful functor from the category of vector spaces to the category of sets that again forgets the vector space structure, but again any linear transformation is a function. So these are defined similarly to the functron groups. I will write down the definition again. these are also forgetful functors. Last week we saw another kind of category, which was categories, a category built from a group, a category encapsulating a single group. So that was the category that had one object and its morphisms were elements of the group. So for any group, let me just say for groups G and H. So for groups G and H, we can consider what it means to be a functor from the category for G to the category for H. Well, a functor, there's only one thing for it to do on objects. It needs to map the morphisms here to morphisms here. Morphisms are just elements of the group. It needs to preserve the identity morphism, that's the identity element of the group. And it needs to preserve composition. Composition is given by multiplication of the group. That's how we defined these categories last week. So a functor is just the same thing as a group homomorphism. So functors are just group homomorphisms, or let me just say homomorphisms. And we also had a way of turning partial orders, or more generally pre-orders, into a category. In this case, the elements of the partial order were the objects of the category, and there was a morphism between two objects, a unique morphism if and only if there's morphism from X to Y if and only if X is less than equal to Y in the partial order. So we turn partial orders into categories, and for groups P and H, the functors from, I don't know why I put an H there. That's a very strange letter to choose for following P. But the functors from the category for P to the category for Q are just, any idea?
Order preserving maps.
Yes, order preserving maps or monotone maps. In my notes, which will be published online, I say monotone bracket order preserving maps. So both of those are perfectly good ways of saying the same thing. So again, the functor needs to map objects to objects. So it's a function. That means it's a function on the underlying sets of the partial order, and it needs to map morphisms to morphisms. So that means in particular, whenever X is less than equal to Y, that morphism from X less than equal to Y needs to be mapped to a morphism showing that f of X, where f is the functor, is less than equal, a morphism from f of X to f of Y, that shows that f of X is less than equal to f of Y. So the map is necessarily monotone, and because there's at most one morphism between any two objects, any monotone map gives a unique such functor. So these are just monotone, also described as order preserving maps. So the moral here is that in the case of considering mathematical structures as categories, which we're doing for groups and orders so far in this course, the notion of transformation of categories, namely functor, gives us the right notion of transformation between those mathematical structures. So category theory faithfully captures the notion of transformation between those structures. Okay. Right, I just want to say a few generalities about functors. So I've just said what a functor is, and I've given some examples. In fact, I don't think I'll even write this. There is a very obvious identity functor from a category to itself. Think how it's defined, but it is completely obvious. And if you've got a functor from C to D, from one category C to another category D, and you've got another functor from the category D to the category E, there's again a very obvious way of composing those two functors to get a category from C to a category E. So maybe I'll just write that. So given, so I've said there's an obvious identity functor, and given functors, so F from C to D, C and D are categories, and G from D to E. E is also a category, G is a functor. There is an obvious composite functor. And it's really obvious. So it's an exercise to think about how to define this mathematically, but it's so obvious that I feel there's nothing wrong in not actually giving me the definition in the lecture. The only thing it can be. There's an obvious composite functor from C to E, early E, G composed with F. One often just writes GF without the composition symbol. And it won't be a surprise, and it's obvious when you write down the definitions, that if you compose a functor with the identity on either side, you get the functor back, and also this composition of functors is associative. So in other words, we have a category of categories and functors. So I just want to be careful how I say this. So we can form a category whose objects are categories and whose morphisms okay. But does this worry anybody? At the moment, I'm not being. There's an issue here. The
category itself is inside itself.
Right. So that's one of the issues. So related to indeed. So basically, I'm going to come to that. Basically, the core thing here is an issue of the size of the categories we're considering here. So because the category, so unlike the usual mathematical structures that we're used to dealing with, like say group, while we're on the subject, groups and partial orders and topological spaces and vector spaces and so on, those are all sets with a bit of structure. And it's not difficult to form the category of all such things, where it's got a proper class of objects, but we've got a large collection of sets, but we can still sort of fit that in our mind. But a lot of the examples of categories we've been considering are at a level above. They're large structures. So now we're going to have actually a category of all categories, including these large structures. And if we form it, then how large is that category of all categories? And is it indeed then an object in itself? Just like, can a set be an element of itself? Can the category of all categories be an object of itself? So let me just summarize this as there are size problems and foundational problems. Now, as some of you may know, I'm quite fond of foundational topics and set theory and so on, and we could actually have a quite long discussion about different ways one can resolve these and so on, but that wouldn't be teaching you much category theory. It'd be more looking at foundations. So we're not going to do that. It raises interesting questions, but for the purposes of these course, I'm going to circumvent the problems. Circumvent is to find a way around. So we shall circumvent problems by considering as our main category of categories category which we're going to call cat. Again, bold cat because it's a category of specific mathematical structures, namely categories. So cat is going to be a category whose objects are small categories, ones whose objects and Hom sets, whose objects form a set and whose Hom collections are all sets. So the category of small categories is the objects and the functors, those are the morphisms. Okay, so this way we avoid the size issue. Cat is a category, but it's not a small category, so it is not it's locally small. We saw that, well, no, we didn't see that last week, but between any two small categories, there are only a set of functors, exercise. And so category is a locally small category, but not small, so it is not an object of itself, cat, the category cat. So cat is locally small, but not small. I just want to make two other remarks about what we're doing. So although cat is going to be our category of small categories, we're still going to consider large categories in the course. I mean, many of our examples, like the category groups and sets and so on, that are not small categories. And we're also going to consider functors between them, otherwise we couldn't get anywhere. So the notion of functor makes sense between arbitrary categories, however large, but when we want a specific mathematical category of categories, we're going to use cat, which is the category of small categories. So that's the first remark. The second remark is that we're looking at the category of small categories as a category here. Doing that actually misses a very important level of structure, which is there are further morphisms between morphisms in this category, so-called natural transformations between functors. We're going to look at those next week. And so this is actually the right way of looking at cat is not really as just an ordinary category, but as something called a two category that has this extra level of structure. But we'll postpone that for the moment. Okay. I'm now going to go back briefly to generalities. Well, maybe these were already generalities, but we're going to continue with let's see, is this the right one? Yeah. I'm going to continue with generalities. I want to think about the examples we've been looking at and notice that they essentially fall into two classes. So our examples of categories fall into two different classes of examples. Examples of categories so far have two different flavors. The first kind is categories whose objects are mathematical structures of a particular kind and whose morphisms are transformations between them, or transformations between them or relations between them. So categories whose objects are mathematical structures and morphisms, summations, relations. So this would be set, group, category of all groups, top, vector spaces, relations, and now cat itself is a similar category. Small categories is a similar thing. And this fits in with one particular philosophy of category theory, which is, when you look at these different elements, each one belongs to a particular area of mathematics. Groups and their homomorphisms, topological spaces and their continuous functions, and so on. And so you can say that the subject area of category theory, from this point of view, are different areas of mathematics. Category is, in a sense, the mathematics of mathematics. Virginia Cheng, who's a famous category theorist, has written popular books about relating baking and category theory, how to bake pie or something. Anyway, she's got some quote saying, whatever mathematics does for the world, category theory does for mathematics. So it's a subject whose category theory is the mathematics, whose the structures you study are somehow areas of mathematics and you relate them to each other. There's actually a very nice video I discovered this week, but it's only 10 minutes long, and I'm going to put a link to it on the course webpage that I recommend. It's called What is Category Theory? It's published by, so I suppose that's got a question mark, it's published by an institute called the Topos Institute, and it's on YouTube. Anyway, I'll put a link to it on the course webpage, and I really recommend you, it's only, as I said, it's only 10 minutes. I really recommend you have a look at that video. Anyway, so this is one philosophy of category theory, but not all the examples fit into this philosophy. So the other one, the other form of examples is categories are categorifications. I don't know how common this word is, or even if it's really a word in the English dictionary, but I've heard people use it before. Categorifications of individual mathematical structures. So when we're turning individual mathematical structures like a group or a monoid or a poset into a category. The examples here were group, monoid, and poset. There's a different collection of examples, and this relates to a different philosophy of category theory, which is category theory as a mathematical subject in its own right that, in a sense, generalizes some existing mathematical subjects in an enlightening way, because one sees constructions in group theory or in order theory, order theory is much more basic in many ways. One sees those as special cases of more general constructions in, and also results, the theorems sometimes, in category theory. And also this philosophy kind of leads to natural generalizations of definitions. So a very important generalization of the notion of group is something called a groupoid, where a group can, from the category theoretic perspective, is a one object category such that every morphism is an isomorphism. A groupoid is then a very natural generalization. It's any category that may have a number of objects for which every morphism is an isomorphism. So these are two sources of examples so far, from generalizing from capturing mathematical areas and generalizing mathematical structures. These ones tend to be non-small categories, these ones are small categories. I'm now going to start, and throughout the course we're going to see lots and lots, well, we're going to see more of everything, but we're going to see lots and lots of this third source of categories. And this is categories formed by constructing new categories from existing categories, or by applying constructions we have on categories. So formed by category theoretic constructions of new categories from old. We're only going to look at two main such constructions today, but they are both very, very important constructions. The first one, from a mathematical point of view, is almost trivial. Nonetheless, it's sort of, sorry, I'm trying to find the right button while I'm trying to think of the right word, and both tasks are failing. Let's try and sit. I've done the button. I still haven't found the word. And now I've lost the sentence. It's been such a delay, so I don't even know where I was in the sentence.
A trivial example from the standpoint of mathematics.
Very good. Yes, it's a trivial. It's a trivial example in the sense that mathematically it's very, very simple. It makes you think. It gives you an interesting perspective. So I still haven't found the word I was looking for, but it doesn't matter. The point is that it's a little bit puzzling in some ways. It turns your world around, literally. So probably most of you, or many of you, know what I'm talking about, having said that. And this is what's called the opposite category. So the opposite, and the definition is really mathematically trivial. So the opposite or dual of a category. For any category C, we define its opposite C op I. Well, the objects of the opposite category are just the same as the objects of the category C, and the morphisms in C op from X to Y. So X and Y are objects of C because the opposite has the same categories. The idea of the opposite category is you simply turn the morphisms around so they point in the opposite direction. You have the same morphisms, but they point in the opposite direction. So the Home collection from X to Y in C op is simply the Home collection in C from Y to X. And the identities, well, the identity 1x in C op. Okay, so I'm putting a little subscript on the arrow here to say this is the morphism, the identity morphism in C op. Well, that needs to be defined. This is in the Hom set C op from X to X. That's the same as the Hom set C from X to X. So we can just take the identity morphism in C. That's just the, sorry, is defined to be the same as the identity morphism in C. Whoops. Oh, well, anyway, that looks like an E, but it's a C, and these should be X's. And the composite, well, if we've got a map F C op from X to Y, and we've got a map G in C op. Sorry, the op should be a superscript here. Don't know why I put that down there. Sorry, getting a bit messy today. Okay, so we've got a composite of F and G in C op. Well, we need to get a map from X to Z in C op, which is the same thing as getting a map from Z to X in C. And we can do that because this gives us we have a G in C and an F in C. So this is defined as the composite F composed with G in C. So in other words, G composed with F in, let's put a subscript C op on the composition. So the composition of G composed with F in C op is just defined to be the composite of F. And the other way around, because we're turning the maps around, composed with G and C. You literally turn the maps around, and then you define identities in composition to agree with that in the original category C, and the only way you can do that's consistent with turning the maps around. That's the way of thinking about it. Simply turn the maps around in a category. And it's puzzling because whereas we're kind of used to thinking of transformations like functions having a direction, we're not used to them thinking of things going that direction being reversed. Well, in many subjects, one does do such manipulations in one's head. But anyway, in a category theory, that one of the beauties of the notion of category is that it allows this very simple definition of a dual notion. It's very simple, but it's actually remarkably useful and remarkably powerful. And we're going to see something of that. Well, not so much the power, I mean, that will come, but we're going to see some uses of the opposite category in the next part. Before going on to that, I just want to make some observations about this, and then we'll have to break. So the first one is that if we take an opposite category and we opposite it again, then we literally get back, it's not even an isomorphism or something, it's literally, by the way, I've defined the same category that we started with. So this is, so oppositing it is what's called a an involution, an operation that if you apply it twice, it gives you the identity. We can think about what happens if we opposite a group. So if we opposite a group, then we get, well, there is, for those of you who know group theory, there is the notion of an opposite group, where you simply reverse the order, you keep the same set and you reverse the order of multiplication. If you've got an abelian group, nothing changes. So opposite of a category, whoops, group. Sorry, that's a, I don't know where that came from. I'm really sorry. And the opposite of a pre-order is, well, there's the notion of oppositing for an order as well, where you turn the order upside down. You simply reverse the relation. It's also called the dual relation. So I think normally that's called the dual. Let's say the dual is the dual order turned into a category. Okay. Right. So that seems to be a good pausing point. So let's pause. Okay. Right. So let's start again. So as somebody pointed out, thank you very much. The definition of a dual category, this bar here just didn't make sense at all. So we're defining the Home collection C op XY, and it's defined to be the Home collection in the other direction. So thank you for that. Please do point, if you notice any issues with what I write on the board, then please point them out. Okay, so we have the notion of an opposite category. We've seen some examples. Functors interact in an obvious way with opposite categories in the following sense, that functors from category C to another category D. Let me just say from functors from C to D are in 1-1 correspondence with functors from the opposite category C to the opposite category of D. Because if you think about it, the information you give to specify a functor from C to D, a mapping on objects, a mapping on the Home collections, you take exactly the same data, that gives you a functor from C up to D up. Same objects and the same mapping on morphisms, only they point in the other direction, but it's still a functor, just a functor in the opposite direction. So this is kind of a nice correspondence. One of the reasons that the opposite category is a very important construction is that it's extremely common that we need to consider functors from an opposite category to a non-opposited category. And this occurs all over the place and is kind of really one of the central notions of functor in category theory. So such functors have a name, which is, so functors from C up to D. We view them kind of as functors from C to D, except that the maps get inverted in the action on morphisms. So these are called contravariant functors, where the contravariant means sort of against the direction of the arrows. Contravariant functors from C to D, and they arise in many, many places in mathematics. And in contrast, ordinary functors from C to D, if one wants to clarify that you're talking about functors where the argument is not an opposite category, they're called covariant functors. So it's the same terminology that one gets, for example, in tensor calculus of covariant and contravariant. So notice I'm going to write symbolically, and I deal with the contravariant functor. Symbolically, I'm always going to put the op in so that we can see it's a contravariant functor. But if I say it in words, I don't put the op here because we already said a contravariant functor, so it's contravariant from C to D. There's not complete consistency in such terminology across the literature, so you need to be a little bit careful. Right, so I want to give an example of a contravariant functor from mathematics. And what I want to bring out is what we called the opposite, also the dual of a category. It's a clear notion of duality in the sense that when you take the, I rubbed it off, but when you take the dual of the dual, you get it's very dual in the sense that you get the dual of the dual, you get back the original category that you started with. The dual categories and the related notion of contravariant functors tend to crop up in many places in which one has dual notions in mathematics. So one of the example categories we're looking at that there's a very well-known notion of dual notion is the category of vector spaces, where one has a dual vector space. So I'm going to show that the dual vector space construction, that's a construction given a vector space, construct the dual vector space, that is actually functorial. So functorial means it extends to a functor on morphisms, namely transformations of vector spaces, linear transformations. However, it's functorial in the contravariant sense, so it's contravariant functorial. So I'm going to, let me use the notes. So recall the dual of a vector space V over a field K is normally written V star, and that's just this, as hopefully most people know, it's just the space of linear functions from the vector space V to the field K, considered as a vector space, if you like. So what I want to show is that that is the object action of a contravariant functor from vector spaces to vector spaces. This is contravariant functorial. As I say, that means it extends to a contravariant functor. So we want to give the object action. Well, I've already told you what that is. So the object action, so we're going to give a function. So the contravariant functorial means we're getting, let's actually write it down, we're getting a contravariant functor from the category of vector spaces opposited to the category, back to the category of vector spaces over the same field K. A contravariant functor from vector spaces to itself. So the object action, we want it to be constructing a dual, but the interesting thing is what we do on morphisms. So it's not very difficult, but part of the point of the next thing, as well as to write it down, is to introduce you to the way one normally defines these in practice, okay? So I'm going to start off with something more complicated than what we write, and then how we then simplify it to what we actually write. So in practice, so the morphism action, we want to say what we do on a map from V, a vector space V, to W. We want a functor in, so we're defining a functor, so we're defining the functor action on morphism, so we want a morphism in vector spaces opposited. And we want to map that to a morphism from V star to W star, so a linear transformation in vector spaces not opposited, because the codomain of the functor here is ordinary, is vector spaces not opposited. So we want to define, given, let's call this map, whatever I call it in my notes for consistency. We want to define something here. But the way one normally writes a contravariant functor is you don't explicitly consider the opposite category, and you don't write arrows in the direction of the opposite category. So the opposite category, formally we know what it's doing, it's turning the maps around, but when you're presenting mathematics, you tend to work as much as possible in the non-opposited category, just so that arrows always go in the right direction and they're not confusing. So the way one normally writes that is you don't bother to put the context here, you simply turn this map around, okay? So we can see what we're doing. We simply have, as an L, it looks like an E. Somehow my writing is particularly messy today, I don't know why. I'm almost tempted to change the letter. Anyway, so it's an L, so it's a linear transformation, and what we need is a linear transformation from the dual space V to the dual space W. It's very easy, so an element of the dual space is a linear function from V to K. So this map here is going to have to map an F, a linear function from V to K, and we want to get a linear function from W to K, and moreover, we want this transformation to be linear. So can anyone tell me what to write here?
Composition.
Sorry?
Composition.
the composition, right? So here we've got a map. We've got an F. We're taking an element of the dual space. That's a linear function from V to K. And we want to get a linear function from W to K, so we're simply going to compose those two linear functions. This is a very, very simple definition. So F composed with L. You can verify this is a linear function, and you can verify that this is functorial. Okay, but it's an example of the functoriality is useful, and I mean we'll use it later in the course, but it is a fundamental fact of the dual space construction, this functoriality. And it's kind of, only becomes apparent what the right thing to do is when you realize how important functors are and how important and the notion of opposite category and the notion of contravariance. Now, I don't want to spend too much time on examples now, so maybe I'll leave it at that. Just want to say something else one could do in vector spaces. So if you restrict to finite dimensional vector spaces, then morphisms can be viewed as, you have the finite dimensional vector spaces, give them with a basis, and you can view the morphisms as matrices, okay? Defining how you map basis elements to linear combinations of other basis elements. You do that, when you've got a matrix going from an n-dimensional vector space to an m-dimensional vector space, you consider the transpose matrix, then you'll get a matrix a linear transformation in the other direction, from the m-dimensional space back to the n-dimensional space. So for finite dimensional vector spaces, that recipe I've just given gives us another contravariant functor from vector spaces to vector spaces that works on finite dimensional vector spaces. That one has an interesting property. It's a contravariant functor that if you do it twice, you get the identity functor. Okay, so finite dimensional vector spaces are actually an isomorphic category to their opposite category via what I just described. This is not even in the notes, but I just thought I'd insert it in. What is in the notes is, and I'm not going to do on the board because I don't want to spend time on it, is a similar example in the category of relations. So a relation from X to Y, you can view it as a subset of the product X times Y. Relations also have a transpose, where you turn the relation around. Every relation from X to Y is a relation from Y to X. And that, again, that transpose operation is a contravariant functor from the category of relations to itself. And again, if you apply that contravariant functor twice, you get the identity functor. So again, relations is isomorphic to its own opposite. It is a self-dual category. Finite dimensional vector spaces are another self-dual category. But this will be enough, I think, for the one example in the lecture of a contravariant functor. As I say, there's another one in the notes. The camera on that board really is a bit blurred. But anyway, I shall try and correct that in future. Right, so I want to, just while on this, before moving on to the next topic, I just want to set an exercise. This could be the weekly puzzle, but it's not going to be. I'm going to have another weekly puzzle at the end of the lecture. But this is also a slightly tough exercise. But it's a really good one to think about. I think it gets progressively harder as it goes along. So the exercise is on Powercept Functors. So to help you to think about one important example. So the first part is find a contravariant functor on the category of sets. And that goes from set op to set. Its object action is the Powercept operation. So the action on objects is take a set, map it to its power set. Remember, the power set is the set of all subsets of the set X. And it wants to be a contravariant functor. The second part of the exercise is to do the same thing again, except find a covariant functor. So let's just take the op out from set to itself, whose object action is again the Powercept operation. And the third thing is to find a different covariant functor with the same object action. This is the second functor. That's maybe a bit trickier. Oops. So these are all three of them important functors in that they crop up in a lot of places in mathematics, particularly the first two, which will probably make them easier to find. But the point of the third one is the curiosity that it exists. I mean, it actually has some mathematical sense to it as well. But also to give you the important realization that if you specify an action on objects for a functor, that's not enough to determine a functor. So one can have really different functors that have the same action on objects, even when that action on objects is quite non-trivial. Right. The next construction I want to do is, I wanted to do, as I said, we want to look at different ways of forming different ways of constructing new categories from old. The opposite construction is a very simple such construction. Let's consider this slightly more complicated construction, but one that's also very, very useful. And ubiquitous in that it occurs in numerous places. This is the product construction on categories. You know, one of the most basic constructions on most kinds of mathematical objects is constructing products of the objects. Product topological space, product group, there are different kinds of product groups, but anyway, there's one actual Cartesian product group. Product of vector spaces and so on. Categories are no different, they have a product. The product of two categories C and D. Actually, let's write it like this. Product C times D, the notation for the categories C and D. It's defined by, you need to define what the objects of the product are. And the definition is not surprising. An object of the product is just a pair of objects, one from C and one from D, an ordered pair. So in other words, the collection of objects is the Cartesian product of the collections of objects of the two categories. And the I'm making the same mistake I made before. It's obviously writing these bars is something I sort of do automatically without thinking. So what do I want to do? I want to say what the morphisms are in the product category from a domain object to a codomain object. So domain object is going to be a pair. So the domain is going to be a pair of objects, one from C and one from D. And the codomain is also going to be a pair, one from C and one from D. And this is again going to be a product of the two Hom collections. There are only two obviously relevant Hom collections here. So there's the X and X prime objects in C. So we product the Hom collection from between X and X prime with the Hom collection between Y and Y prime. Sorry, yeah. So a map in C in the product category from XY to X prime Y prime is a pair consisting of a map from X to X prime and a map from Y to Y prime. And the identities and composition are again obvious. Let's write them down anyway. I mean, I keep on saying things are obvious, and please actually email me or let me know or come and harangue me after the lecture and tell me that these obvious things are not obvious. I mean, hopefully so far they have been. Or come and tell me that actually everything I'm writing is obvious and I should be going 3 times as fast as well. But I think we have to do things. I think we have to do the basics, and we will. Anyway, let's actually write it down. So what I want to do is define the identity on a pair XY. Well, that is it's a pair of maps, one from X to X, one from Y to Y. So it is the pair consisting of the identity on X and the identity on Y. And the composition of a G of a pair let's make it consistent with my notes, of a pair FG with another pair F prime G prime. So to define that, well, here we've got, so when we're defining the composition, we've got on the right, we've got a map from, so here this is going from, say, X, Y to X prime, Y prime. My primes are going to get a bit unpleasant in that, anyway, but never mind. Here we're going to X prime, Y double prime, and here we've got FG, and here we've got F prime, G prime. And that means that in C, so this is in the product category. So in C, we've got the map F from, we've got maps F prime and F from X across to X double prime, and maps G prime and G all the way across like that from Y to Y double prime. That's Y prime in the middle. Anyway, so you obviously just compose the components. Okay, so the more you try to unpack it, the more complicated it looks, when it's really like the simplest is really something very simple, which I hope you agree. And it is easy that this defines a category. You can check that if you like. Not only does it define a category, but there are evident functors. I'm going to write it on. Let's put functors. But from so from C times D, there's a functor that takes us to C that just takes the first component of all pairs, both objects and morphisms, and from C times D, there's another one that takes the second component of both pairs, and that gives us a functor to D. And these are like the things we used to have associated with products, these are projections from the products. So they're called the projection functors, and we often call these pi1 and pi2. Pi, because it's a Greek letter for P, and we're talking about projection functors. So that is the product category. I tried to draw a picture of it, but I was trying to think about that, and I couldn't quite see a good way of drawing a picture. But the idea of tuples of things, well, pairs of things and pairs of maps, is perhaps doesn't require too much. It's not that complicated to visualize. And then having understood this, one can generalize this to finite products. So I don't want to write out the details, but it's kind of obvious now how to do it. So the product of finitely many n different categories. Why stop at finite? I mean, in fact, for any family of categories, we can form the same recipe will give us a product. And more generally, if we've got a family of categories indexed by some index set capital I, so the little I index comes from capital I, we can form the product category over of all the categories we're indexing. Okay. And more generally, index products or arbitrary products. One of the main things that's useful about product categories is it allows us to define the notion of a multi-argument functor on categories. So not just a functor from a single category to another category, but a functor that takes multi-arguments of many different categories. Sorry? Yes, it did switch, but at the same time I pulled the battery cover off the remote control rather clumsily. Right, so we've got this far, and so it's now clear what is meant by. It's now clear, at least mathematically, we haven't seen any examples, what is meant by a multi-argument functor. A multi-argument functor from a product of categories. So it could be an arbitrary infinite product as well, but that's normally finitely many arguments are enough. So product of categories C1 through to Cn to D. So I can do that either as a functor from the product category, that's the mathematical definition, but we view it we think of it as a functor that takes n different arguments, each of which is a category. Okay, and I don't need to write out the definition because you've understood what a finite product is the natural generalization of the binary product. In fact, you can encode finite products using binary products just by pairing things up sufficiently often. And now we know what a multi-argument functor is. So the last piece of content I want to end with today, before, oh no, not quite. Oh no. Oh, that's again. We have a saying in English about getting out of bed the wrong side in the morning. So I think I got out of bed the wrong side this morning. In fact, I seem particularly clumsy today. Also in what I'm writing. Anyway, so I want to end with one very good example, not quite end, but I want to write one very good example of a multi-argument functor. Very good because it is a really important functor in category theory. And we almost know it. We know its object action. So we just need to understand its morphism action. And this is called the Home Functor. So this, for a category C, this is, we normally write it like this. So it's a functor, maybe I'll stay on this line. It's a functor with two arguments, and you often just write, so you just write the arguments as, like with placeholders, so a dash, meaning it's a placeholder for where we put the argument. And notice I'm calling the functor C brackets, and that's because of how it's going to be defined. It's going to be the Hom collection. But what's important about this functor is what its domain and codomain is. A two argument functor. It goes from the product of C op and C to set. To get into set, we need it to be a locally small category. So it's defined by, well, the object action is we need to define what this functor does if we feed it to two objects, x and y. So we need to define this functor applied to the objects x and y. What's that going to be equal to? Well, why did I choose this notation? Because what it is, the functor applied to sets x and y, sorry, not sets x and y to objects x and y, is simply the Hom collection from x to y, which is a set because the category is locally small. So this is simply defined to be the Hom collection, the Hom set, because it's locally small, C, x, y. So the notation is not misleading here. So that's the object action. What about the morphism action? So we're going from the product category of the opposite times C. So the morphism action needs to tell us what we're going to do on a morphism G in C op from x to y. Sorry, in C op from x to x prime. So a morphism G in C op from x to x prime. Remember our conventions. We write morphisms in the direction they arise in C. So morphism from x to x prime in C op is a morphism G from x prime to x in C. Okay, this is from x to x prime in C op, and a morphism from y to y prime. Let's call this H in C. Okay, so we've inverted this one because the first argument is in the opposite category. And we need to map this to a function, because we're in the category of sets, from the set of morphisms from x to y to the set of morphisms from x prime to y prime. So what's this function? Well, it's going to take a morphism from x to y, f, and map it to, okay, can anyone fill in? We now need to get a morphism from x prime to y prime. So f is a morphism from x to y. So how do we get a morphism from x prime to y prime?
First we go with the G, then we go with F, and then we go with H.
Right.
We compose them.
So we compose them. So it's not so different from what we did with vector spaces. There we go. Compose them G, F, H, which when you write it using the composition operation, you write in the other order. Okay, and that is a functor. So verify that this is a functor. It preserves the identity. If you give it two identities, a pair of identities here, you get the identity back, and it preserves composition. And this part here, the functor, we say it's contravariant in its first argument and covariant in its second argument. Okay. Right. So none of this is technically very difficult. It's just quite abstract. So one of the issues people have when they first meet category theory is it's quite abstract. Home functors, I mean, you can think about what they're doing in particular cases. I mean, they're going to play a really important role in this course. So it's very important that you understand this definition. So think about this. If you've got any problems with it, this is another big exercise for this week, is really think about and understand this definition of this functor, because it's fundamental. Right. So I want to now end with something just a little bit different and maybe a little bit less abstract. And some very important, I mean, I'm saying everything's very important. That's because we're doing fundamental things. And when you do fundamental basic things, they're all kind of important. Everything's going to be built on them. But this is now important. What I'm about to do is also important in a sort of philosophical sense of part of the power that arises from having the dual construction, the opposite construction in category theory. It gives you a really sort of nice, powerful tool in the following way. So I'm going to call this, this is an example of what we might call exploiting duality, the fact that categories are self-dual, and we can use that fact. And the idea is that if we have a category theoretic concept, then whenever we have any category theoretic concept, we for free get another category theoretic concept by interpreting the original category theoretic concept in the dual category. Okay? So I'm going to give an example of this, which is the dual notion to the notion of monomorphism. So last week we had the notion of a monomorphism in a category. And now we're going to have the dual notion to the notion of monomorphism in a category. And this is called an epimorphism. So the quick definition of the notion of epimorphism, a map f from x to y in C is an epimorphism, or epi for short, if it is a monomorphism in C op in the dual category. So this is what I mean. We understand the notion of monomorphism. It makes sense in any category. We can therefore look at it in the opposite category. What is a monomorphism in the opposite category? Well, we'll call those the maps that are monomorphisms in the opposite category, we'll call epimorphisms in the category we started with. So if it is a monomorphism, that's short for monomorphism in C op. Well, that's nice because it's a really quick definition. Of course, we can simply expand the definition of what it means to be a monomorphism in C op and get a definition of epimorphism that does not refer to the opposite category. So expanded, let's do that. Expanded x fy is epi if, well, remember, it was a monomorphism if for all parallel pairs of maps into X, if the composites with F were equal, then the pair of maps themselves were equal. So the opposite, well, we're going to look at maps into F in the opposite category. So maps into F in the so it's coming in towards F in the opposite category, while in the opposite category, F goes in the other direction. So it's maps, so we're going to have maps into Y in the opposite category, or maps out from Y in the starting category. So the dual notion gives us for all pairs of maps coming out, parallel pairs of maps coming out of Y. So for all maps, let's call them G and H, pairs of maps, G and H to some common codomain Z. So again, this is saying for all Z and for all pairs of maps G and H coming to Z, we have the same implication that we have for monomorphisms, which is that if G composed with F equals H composed with F, then G equals H. So the expanded definition is both longer, it's unnecessary because we've already defined what it means to be an epimorphism. But the shorter definition also has the following advantage to it, which is because we've defined epimorphism by duality, whenever we prove a property of monomorphisms, we at the same time prove the dual property of epimorphisms. So for example, we had the property last week as an exercise that if you have a pair of maps and the composite is a monomorphism, a pair of maps going in this direction, and the composite is a monomorphism, then the left-hand map is also a monomorphism. That was one of the properties last week. The dual property is if you have a pair of maps and the composite is an epimorphism, then the right-hand map is an epimorphism. That follows for free from the result we already have. It was an exercise last week, the monomorphisms. Okay, so just want to tell you a little bit about epimorphisms, a very little bit. I'm not going to be as thorough as I was last week about monomorphisms. So in set, the epimorphisms are, anybody know? Surjections, yeah, surjective functions. We saw in lots of categories the monomorphisms were characterized as injective functions. If you look at those examples, it's true for topological spaces that the epimorphisms are the surjective functions. The other examples, well, in some other cases too, but in general, it's less true in general in the examples we've been looking at that epimorphisms correspond to surjections. You can think about that in other categories. Before I get to, I'm about to set the week 2 puzzle, but before I get to that, just one other remark about surjection. So one's used to dealing in set theory, you have the notion of bijection, injection, and surjection. But when you define those notions in set theory, it's not really clear in what sense the notion of injective function is dual to the notion of surjective function. The definitions look really quite different of being an injective function and surjective function. The nice thing about the category theoretic definition is it really tells us that surjections are really an precisely dual notion to the notion of surjection. So surjections and injections are precisely dual notions. Anyway, having got the notion of surjections, let me end with the week 2 puzzle. So again, it's a bit challenging, but the idea is to give you challenging puzzles to hopefully stimulate some of you to think about things, and they all need a little bit of lateral thinking in some sense. You need to have some idea to solve them. So the week 2 puzzle is, does every functor, endofunctor on set, an endofunctor means a functor from the category to itself, so does every functor from set to set preserve monomorphisms? What does preserve monomorphisms mean? Well, it's defined in the notes, but it says the morphism part, if you start with a monomorphism, do you get a monomorphism back when you apply the morphism action? So, and the second question is, the same question, but with monomorphisms replaced by epimorphisms. So does every functor preserve, if you wanted to set theoretic terminology, does every functor preserve injective functions, or does every functor preserve surjective functions? Okay. That's everything for this week. If anyone's got anything to discuss after the lecture, I'm going to stick around for a bit, so you're welcome to do so. Yeah, okay, so that's all right. So I'm going to stop the recording now.